this video is going to be about how do we handle integration with exponential growth. So before we get started, there's a couple things I want to review just about exponential growth. So in pre-calc, you should have learned a formula for exponential growth where it was some constant. I'm going to use C because that's what we've been using. E, and then I have K is a rate of change, and T is amount of time. And then K, right here, if K is negative, we've got decay, meaning it's decreasing, and if K is positive, we have growth. So that's really what we're looking at. We're going to start with the derivative, and we're going to build back up to that formula and see how we get there. It's important to remember that K is just a number, it's not our variable. C is also just a number, it's that constant scalar, the initial amount. So we're going to start with separating the variables. Again, K is a number, Y is the variable. So I'm going to move Y to the other side. So I have 1 over Y dy equals K dt. From here I'm going to integrate both sides. So 1 over y is going to become ln, so I have ln y equals, this time it's going to be kt plus c. So now I have to look at this and I have to say, how do I clear ln? What do we do to get rid of ln? Because I'm trying to solve for y. All right, hopefully you indicated that we're going to use e. We're going to use e to clear ln. It's called exponentiate. So now we have y equals, and this is an exponential formula, so that plus c, that's like e to the c. We're going to move that in front like we've been doing in our last several topics. C E K T, and so that's going to build us right back to that formula that we started with talking about from pre-calc. So this is our derivative formula. There's going to be some key words to look for. One of the key words to look for here in example 2 is where it says directly proportional. When you see those words directly proportional, that is going to be a clue to you that we are talking about exponential growth or decay. So in this problem, we're going to take, it says we have bacteria that increased from 400 to 1600 in 3 hours. So I'm thinking about like hour 0 was 400. Hour 3 was 1600. And it says, assuming that the rate of increase is directly proportional. So that's telling us that it's going to fit this equation. So what we need to do is we need to build the actual equation from the information given. To do this, I'm really going to use more of a pre-calc strategy than calc, because if we understand the words directly proportional means exponential growth, here's what I know. I know that this initial value, that is C, and then I can say this is a T and a Y, and I can use that to solve. So I'm going to start with 1600 is equal to 400 E, K, and I know that the time was 3. And so what we're doing is we're trying to solve for K to write that equation. So you're going to take a minute here to solve for K. All right, we're going to divide the 400 off, so we're going to get 4 equals E3K, and we're going to have to clear E with ln. That's going to clear it, and divide the 3 off, so K is equal to ln4 divided by 3, which means to write this equation, I can put K back in. I have y equals 400 E ln 4 divided by 3t. So that's our equation. Part B says find the number of bacteria at the end of 6 hours and to use a calculator. So you're going to pick up your calculator and you're going to plug in 6 for t. So we're going to put in the calculator 400 times E. Make sure you put everything in your exponent, ln 4 over 3, and then times 6. And let me know what you get in the calculator. Right, hopefully you said 6,400, and that is bacteria. There's another way to kind of more or less cheat this. If you kind of skip count, notice this is counting by threes. So if I came here and said 3 more, that would be 6. And then what did this do right here? This said times by 4. So right here is times by 4. So you can go back to your pre-calc strategies just to kind of rationalize through what these problems look like. All right, example 3 is not as straightforward. So we need to revisit from pre-calc what we mean by this half-life. Half-life is literally the amount of time it takes for something to decay to half the initial amount. So when I do half-life, I'm automatically saying, like, we start with y equals c e k t. C right here is the initial amount. And so when we talk about half-life, it means like whatever was there, in this case it says 100, is going to go to half. So I just automatically start with 1/2 equals E, K, and it says that it takes 1590. You're going to get the same thing as if you were to start with the 100. You'd have to cut it in half, call it 50, divide the 100 off. You'd still end up with this 1/2. So what I tend to do is I tend to just start when it says half-life. I just start with that fraction and ignore the fact that C was there. So now we're going to have to solve for whatever K is. We have to have our rate. So I'm going to change 1/2 to 0.5, just because it's a little bit easier. And we're going to ln both sides to clear E. So I have ln 0.5 equals 1590K. And we're going to divide 1590 off. So we have K equals ln 0.5 over 1590. That's our K value. You're going to want to, or feel the desire to, I should say, change that into a decimal, but we should not do that until the very end. We want to make sure that we don't cut off decimal places and round our answers until the very end. So our formula is y equals, since we're starting with 100, E, and we just found K, so ln 0.5 divided by 1590 T. So find the mass after 1,000 years. So again, we're going to plug in 1,000. This is one that we can't benchmark. So the other one was easy to benchmark because it was counting by threes. This one is 1,000. We know that's going to be more than half because the half-life is 1590 and this is only 1,000. So thinking about that should help us kind of rationalize through whether or not our answer is right if we put something wrong in the calculator. We always want to think about what answer should we be getting. So times by 1,000. We're going to put this in the calculator and go ahead and let me know what you got. All right, I got 64.666, and this is measured in grams. If you didn't get that, you probably put something wrong. My guess is in your exponent. Make sure that whole thing is in your exponent. You might have to use some parentheses to make sure it's in there. And then question C is, when will the mass be 30? So this time we're solving for 30 equals. So I'm going to say 30 equals 100 E ln 0.5 over 1590. And we're solving for T. So I'm going to have to divide the 100 off. So 30 divided by 100, I'm going to say 0.3 E ln 0.5 over 1590 T. And now I need to clear E. How do we clear E? Well, we're going to use ln again. So I'm going to do ln on both sides. It's going to clear E. So now I'm left with ln 0.3 equals ln 0.5 over 1590 times T. Then we're going to need to move the 1590 over and divide by the ln 0.5. Or you could think of it as just flipping that, take the reciprocal of that ln 0.5. So we're going to have 1590 times ln 0.3 divided by ln 0.5. We'll put that in the calculator and we're going to get a certain amount of years. So let's think about what kind of answer we should get. So 30 milligrams is definitely less than half, so it's definitely going to be more than 1590. I get about 2,761.775 years. If you didn't get that answer, you probably have put something in wrong. My guess is where that division falls. So let me know if you have questions, and we will do some more examples in class.